Our next speaker is Emmanuel, who will tell us about DanceCam.
Okay, thank you. Thank you for having me. So I wanted to share with you some insight about what would be the potential of video imaging at CFHT. This is something I started presenting something in the last users meeting, but since then things have moved on, and I will show you some results. Okay, so the DanceCam project, it's actually a kind of small projects that we had, and these are the people with whom I have been working on this over the past year. So it's a small project where the original goal was to leverage new technologies, including new detectors and deep learning, for instance, to improve the efficiency of those small telescopes. So rather in the up to 1 meter class, so not like CFHT. So the main application is for those telescopes engaged in surveys in time domain, trying to identify counterparts, for instance, of energetic sources, and try to improve their efficiency in all kinds of conditions. So now my talk will be about how could that help with larger telescopes such as CFHT. So just a small reminder, all this is possible now that because we have this new technology, new large detectors, which unlike CCDs have much lower readout noise, and you can read them very quickly, very efficiently. There are some issues with them. They are not, for instance, the homogeneity is not as great as with CCDs, but it has been demonstrated recently that it's not an issue with for current research programs. And I would like to stress that although the readout noise is much lower than CCDs, it's still the ones we can find commercially are still a bit too high compared to what you would need not to degrade the signal to noise by moving to video. So, but we're getting there, and in the labs you have already models for which the readout noise is completely negligible. But so we're getting there, but so it's time to get ready for these new types of detectors. And so it's also in the context, and Samantha told us about this morning. She reminded us about this huge increase in the quantity of satellites we have on low orbits, to currently about 15,000. This is not counting debris, and there is already 1 million which have been filed, 1 million project for such satellite which had been filed at the International Telecommunication Union. So it's really getting an issue. It's an issue, and of course, moving to video will really helps. Obviously, you're doing wide field. So this is an example here that you can see. I hope you can see the video from where you are. So this is a little wide field of view, which is quite comparable to what you have on Euclid, and it was obtained at the Cairn Observatory at C2PU telescope, 1 meter telescope. And this is with just 5 images per second. You can see that low orbit satellite, you just get those small streaks. It's very easy to filter out from your video streams. And even if you have, plenty of those satellites crossing your field of view, you can manage that clearly. Now, there are other benefits to deep sky video imaging. You have this ultra short readout time, which is completely negligible. So no shutter, so no time loss to reading the CCD. And in the case of MegaCam, it's between 10 and 60% of the time on sky, which is spent on reading those CCDs. Hopefully, most of the time, you have overheads which take advantage of this, but still. And no guiding also is required, which is also interesting in difficult conditions, when you have those TOO and less than ideal situations, and you don't want to lose time on trying to reach the guide star and so on. Also, another point which is very relevant to what is being done at CFHT with MegaCam is that currently, if you look at typical night observing with MegaCam, you can have typically up to 25% of exposures which are non-sidereal guided. It means that those exposures, even if they end up being archived, they would be useless, basically for people not interested in a very specific objects because they are trailed. And with digital stacking, with video imaging, you can make 2 kinds of stacks. For instance, you don't want to store the data because it would be too large in video mode, but you can make in real time 2 kinds of stack, one which would be sidereal guided, and the other one which would follow the prescription of the observations. And of course, it brings you free monitoring, photometry at even better than Sky Pro potentially. And also it has been shown that you could actually do real-time tomography of the turbulence through the atmosphere if you have a sufficient sufficiently wide field of view by looking at the correlations between the apparent star motions. And of course, one of the important aspects, which I'm going to detail now, is the possibility to mitigate the blurring effect from the atmosphere. So amateur astronomers, they know very well that with small telescopes, in a regime where your aperture is a few times the Frick parameter, you can really improve the image quality by looking at instantaneously at images, or trying to adapt. If you want to stack, you need this to distort the images to follow the distortion of the apparent distortion of the images. And this is the so-called rubber focal plane model, which was theorized by Kaiser, Tolvey, and Lupino in 2000. So they had this project with pan-stars actually to improve dramatically the image quality by using, at the time, it was a special types of detector, and so the OTCCD. Unfortunately, this did not work as intended, but now things are much easier because we can process things completely digitally thanks to those CMOS detectors. So another point, when you can move, if we work with larger apertures where we have many Frick lengths over our pupil diameter, we enter another regime where the shift and add procedure becomes not as efficient, and there is still a way to recover almost diffraction limited images if your images are properly sampled both in time and in the angular domain, is to do holographic reconstruction, which is a process which is almost linear, actually with respect to the images, except for the point space function itself. And if you have a very good model of PSF, you can really get amazing images. This is an example from Shodel 2013 on real images. Actually, this is from images coming from adaptive optics. And so the typical use of this is with GLEO. So it's a kind of post-processing of GLEO images using very short exposures. And the challenge here is to track the PSF, which is difficult with short exposure, which are disconnected in time. But with video imaging, you can benefit from the history as layers, they pass through the pupil, and you can expect to recover a much better PSF model using, for instance, deep learning. Another context also is now the advent of those shortwave infrared detectors, that have a flat QE almost from blue to up to the H band, more than the H band, and with tiny pixels. So if you put, for instance, one of these detectors at, let's say, for instance, the f/8 focal plane that Olivier was discussing earlier, this is I just made a simulation with the library that we wrote for this project. And the H band, for instance, this is on the left. This is what you would get with, for instance, with rear cam, or with a camera with 30 millisecond pixels. That would be what you would obtain with such detector. So you would get this with rear cam with heavy dithering, of course. It's a bit better than what you would get with rear cam. On the middle, you see what you get when you do shift and add. So this focal plane, the rubber focal plane model. And if you go all the way to holographic reconstruction, you end up with images which are diffraction limited. So I want to stress first that this simulation included they are realistic with isoplanetic distances and so on, 5 layers, the typical Frick parameter that you get at CFHT. But there is one catch here, which is very important. Between the image on the center and the image on the right, you don't get improvements in signal to noise for the sources. That is very isolated. If you want, for example, to measure their magnitude or their position, and they're perfectly isolated over homogeneous noise, you won't get any significant improvement. But when it's all about morphometry or deblending sources in crowded environment, of course, it's really an improvement. Okay, so just one thing to present is so we wanted to test the concept of using deep learning, but to image reconstruction, but going directly to image reconstruction straight from the video sequences. And this work was done by Spencer Benek, who spent some time a few years ago at CFHT in a technical internship, and so he came up with a neural network model that was able to it was trained on COMFAR, by the way, that was able to reconstruct images from video streams. You see here an example in 2 cases. So the training was done using our simulator on a range of type of scene on a given telescope, 1 meter. And you can see here the video frames, of course, which are just extracts from these simulated videos. You see the sliding average that you would get from, stacking 6 seconds of videos here on the third column. And the fourth is the reconstruction that you get using this deep learning model, which was very promising. So, of course, the challenge was to apply it to real data. So we had a small sequence that we managed to get once again at the Calern, at the C2P Omicron telescope there. And you can see that it was really something which was really important for us. It's a video actually here, and you can see how it slightly evolves. So this is what you would get with SimStack. We were quite pleased to see that with a simple forward model of the atmosphere, it was realistic enough for the neural network to be able to correct the images even without domain adaptations or stuff like that. So it's really an achievement. And you can see the result that you get in terms of width and the stride ratio. And we get an improvement in these very early results. We get an improvement in the completeness at a given reliability level. But of course, once again, we don't increase really the depth at that level because the images were not, really, so we are not in the regime of being tilt dominated. So just to conclude, I believe that high cadence video imaging carries a lot of potential for wide field imaging. So there's no way you can store these images. And if you would store the images, you will end up with hundreds of time. For instance, with alpha degrees field of view, you will end up with hundreds of time what the LSST will be producing per night. So it's really not really reasonable. So the idea is to do it in real time or quasi real time. It's a solution for mitigating the impact of satellite, monitoring the sky, improving the image quality whenever possible. And I think it would work best in combination with ground layer adaptive optics, because then you enter more in a regime which is tilt dominated in the end. And so residuals are right of tilt dominated from the higher layers. And so we have to watch out, of course, for DCR, so work rather in the red, because we are working such at a high resolution. So unless you have, of course, DCR correction. And so once again, you get specular improvements when you move all the way to holographic reconstruction, but it's mostly about crowded fields more than isolated fields. And the key is really modeling the PSF. So deep learning is really a way to go here, because it's able to take into account, what happens over the video, over parts of the images, so the spatiotemporal cues. And what remains to be assessed really is the impact of undersampling, because working on such a large field of view without, with comfortable sampling is not necessarily an issue. It's not necessarily reasonable. And of course, what happens with optical aberrations, and because we might not be totally limited by static diffraction. Thank you.
Okay. Well, let's thank Emmanuel.